All right, so let's get into a section about applications of exponential and logarithmic functions. Okay, this is called exponential and log models. So the first thing we want to look at is exponential growth and decay. I talked about growth and decay and some examples of this in a previous video. So you may remember I explained about how exponential growth is used to model things like population growth, and exponential decay comes up in things like radioactive decay, but also I mentioned something about heat cooling. Heat, not cooling. No, actually cooling is the right word, yeah. Temperature cooling. We're going to get to that application in this section. So first, let's discuss exponential growth and decay. Growth and decay generally happen continuously, and so in this section, we're going to come up with models for growth and decay which use the natural exponential function, which is the most natural model to use when you are working with continuous growth or decay. The function model we can use to model growth and decay is a function of time, f of t, equal to some initial amount, a0, it's your initial quantity that you start with at time 0, times e to the power kt, and that's where k is the relative growth rate or decay rate if you make it negative. So here in this model, a0 equals the initial quantity, k equals relative growth rate or decay rate, depending on the value. And this is, by the way, exactly the same thing as PERT, P e to the RT. It's exactly the same thing, it's just in this section, different letters are chosen to represent the parts of the equation. Okay, so we break this down into two cases. In the first case, if k is positive, then that's when you have growth. If k is positive, then we have growth. If k is negative, then we have decay. And we can understand that now because this is kind of like the base is e to the k, all right? And if you take e to the k and raise it to the power t, then you can simplify that by multiplying the k and the t together. But e to the power k would be the base of this exponential function. And if k is a positive number, e to the k is going to be bigger than 1. But if k is a negative number, e to the k can be less than 1. Positive e to the k is growth, and negative k value giving us an e to the k less than 1 would be decay. So now that we've learned about those properties of exponents and talked about positive and negative powers and all that jazz, then we can understand that a little better now. So this means that, in fact, any exponential function with any base can be rewritten in terms of base e. Okay, so we can always use base e for this sort of thing. Let's look at an example. So for this example, let's talk about growth. And suppose for this growth that the doubling time, the time it takes for something for the value of the quantity to double, suppose that time is 5 hours. Let's find the growth rate, the relative growth rate. Okay, doubling time is the amount of time it takes for it to double. So if we take our model a0 e to the kt, if we set that equal to double the initial amount, 2 times a0, the amount of time it takes to double from starting from t equals 0 when it's a0, the amount of time it takes to double to 2 times a0, that should be our doubling time. So setting up this equation, if we solve this for k, then we should be able to find the growth rate. Now there's one piece of information I haven't put in here, which is that the amount of time it takes for this to happen is 5 hours. So I should put in t equals 5. So I'm going to replace this with a 5. There, I kind of fixed it there. So it's k times 5. All right. So put in the specific amount of time, and now we're going to solve for the k. Now technically there's two unknowns in this equation. There's k and there's a0. But you'll notice that we can divide both sides by a0, and the a0 cancels out in both cases, so the actual specific value, the specific initial value, doesn't matter. It just cancels out of the equation, and it turns out it doesn't matter what we started with. The point is that it's doubling. That's all that matters here. So now we have e to the power 5k equals 2. So for the next step, what I want to do is try to cancel out that exponential function. So what I can do is apply natural log. Since this is the natural exponential, I'm going to apply the natural log to both sides. Okay, what we're doing right now is we're just solving this exponential equation. And on the left side, the natural log and the exponential, will cancel out, giving us 5k. And we have that's equal to natural log of 2. And then our k is the natural log of 2 divided by 5, which is approximately, oh, I don't know what that is. I forgot to calculate it. It doesn't matter. Calculate what that out is with a calculator if you want to, and you can get the value. You can approximate that value to whatever you would like. Natural log of 2 over 5. So what you'll notice is we ended up taking the natural log of 2 just divided by the doubling time, right? So let's generalize this. Okay. If we have doubling time equal to some value, we'll call it capital T. Okay, Tim. Doubling time is capital T, all right? We had a0 e to the k times t equals 2a0. We canceled out the a0s, right? And we did kt equals the natural log of 2, and we divided by t, and got k is the natural log of 2 divided by the doubling time, right? So generalized, we're always going to get exactly this, right? So we can write down this nice simple formula in general. If doubling time is t and growth rate is k, k always equals the natural log of 2 divided by t. And so that is for growth. Okay. Growth. You can write down a similar formula for decay. Except for decay, instead of doubling time, you have half-life. Let's say our half-life is equal to h for half, sure. And again, our growth rate is k. We should expect that to be negative this time, by the way, because we're talking about decay. So we're going to have negative growth rate there. Then that k value is going to be, this time, the negative natural log of 2 divided by h, the half-life. Okay. Another way to write that, by the way, is the natural log of 1/2 divided by h. And these are the same. Because the negative natural log of 2, if you take that negative 1 and you make it a power inside of the logarithm, you get 2 to the power negative 1, which is 1/2. So these, knowing our properties of logarithms, we can see that these are actually the same thing. Okay, so these are some nice formulas you can use, and they can convert between the relative growth rate, or relative decay rate. Sorry, that was meant to say decay rate. It can convert between that k value and either the doubling time or the half-life, depending on which one you are working with, which type of function you're working with. Okay, so if you're given one of these two pieces of information, you always calculate the other. You can always calculate the other using these formulas.